All right, so now that we have components of f1 plus f2, the resultant, and of f2, what we can do, actually, something I just noticed is that I sort of forgot to check this before, but now that we see, if you just notice, in this area here, 40 and 50, these angles would add up to 90, which means that this would be a 90-degree angle triangle with f1. So we probably could simplify the process because this just happens to be 90 in here. So if you want to kind of go about doing the question a little bit differently based on that, you can. But I'm going to kind of pretend that that didn't happen here, because the more complicated solution is probably the one you need to see more examples of anyway. So if one of those was 41, the other one was 50, we couldn't assume it was 90. We couldn't use, Pythagorean theorem or SOHCAHTOA or whatever. Okay, so let's just continue on, kind of ignoring the fact that that is exactly 90 and doing this as if it was any other angle. Okay, the next step here would be, so if you look back at this line, we want to add the opposite of f2 to f1 plus f2, which means that we should have the components of the opposite of f2. Now, they're pretty easy to get, right? The opposite of f2 is just the components of f2 with the opposite sign, right? Meaning that the horizontal component would be positive 9, and the vertical component would be positive 10.7. Okay, so then if I actually take this equation, we actually compute it, we actually sub in values for it. Then we're going to go with, so we're taking the components negative 7.7 and 6.4. So these are the components for f1 plus f2. And we're adding to it components here, 9.0 and 10.7. And this is equal to f1 bar. So we should have 1.3 for x and 17.1 for y. This is f1. Cool. So again, what does that mean? What does this actually tell us about f1? So our f1 vector, if we look back up at our diagram up here, is this red vector. Okay? If I just kind of duplicate it to bring it down. So this vector component statement tells us some useful information. And it just sort of line up with how we've drawn this, right? This looks pretty nearly vertical with a very slight horizontal piece to it. So if I compare the horizontal component size to the vertical component size, it's much more vertical than it is horizontal. Okay, so if I represent this here, our 1.3 horizontal component is going to be this little piece horizontally combined with, a nearly, this is vertical, 17.1 vertical piece. Something like that for the diagram. We're trying to be as close to scale as we can be. Okay, something like that. So just to label some things here, this is our f1 vector, this is our y bar, and this is our x bar. Okay, so if we're finding the magnitude, again, this is a 90-degree triangle, finding the magnitude and the direction which we want the bearing for, we can do this pretty easily now that we have a 90-degree triangle question. Okay, so let's start with the magnitude of f1. We're going to use the Pythagorean theorem type thing, because this is a 90-degree triangle, we have these two sides. So the magnitude of f1 squared will be the horizontal component squared plus the vertical component squared. That's just Pythagorean theorem. These are the two perpendicular sides. This is the hypotenuse. So pretty straightforward. Let's use calculator, 1.3 squared. 294.1, and then we square root it. So the magnitude of F1 bar is about 17.1 meters per second, I believe. Yeah. So that's one of the answers we need. We also now need the direction, bearing, I guess. And so this was for magnitude. And now we're going to do for the bearing. So if I go back up to my full diagram up here, bearing, remember, starts at north and goes clockwise. So ultimately, I'm interested in this very tiny angle in here. If I could draw, in there. I want this angle, right? How much clockwise of north is this line? Now, if I look at the 90-degree triangle that I've created with the components, the interior angle I can find is this one here, right, between the horizontal and F1. I can find that angle, and then just subtract from 90 to get this small little piece out here. Right, that's basically what we want to do, is find the interior angle, subtract from 90, then we have the bearing. Okay? You can use primary trig to do that. So we're going to go with tan, because tan uses opposite and adjacent. Those are the components that I have. Tan of theta, theta we don't know. That's what we're finding out. Is opposite, that's y, 17.1. Over adjacent, that's 1.3. Theta equals inverse tan. We get 85.7. So remember, we need to subtract from 90. And we have our bearing. 4.3. Right? So as a bearing, remember, it needs to be 3 whole number digits. So that would be 0, 0, 4.3 degrees. There we go. So pause it here. You need more time, but we're going to proceed on to the next question to try to reduce the number of videos we need to finish this. Okay, same type of question. I really, really want you to be able to do this type of question. So we'll do one more example of it here, just so you have lots of examples to reference off of. Okay, so again, let's highlight the important stuff. We are given F2 has this magnitude, and it has this quadrant bearing, and the resultant has that magnitude and that bearing. And we're given actually one more piece of information. We're given that F1 has this magnitude. The question is, what is the bearing? So let's just find out the direction of it, is really all that we're interested in here. So we're going to do it the same way, except that we can skip the magnitude part and just go right onto the bearing part. So there's one piece we don't have to do. So let's quickly draw this out on our diagram here. So F2 is south 45 east. So starting at south, go 45 towards the east. Like that. 0.3 newtons, just small. And then F1 plus F2 is 260 degrees from north. Right over here, it's 2, quite a bit longer. So you can see that that's not a 90-degree triangle. So let's proceed in doing it that way.